All right, so then the next talk is by Marko Znidaric, and well, he'll tell us about non-hermiticity and anomalous relaxation, the sloppy part.
Yes, thank you, Leah. Yeah, title is a bit mysterious intentionally. So I will speak about something we came across about 3 years ago. It has to do with non-normal operators. There are some funny effects, and the title is alluding to that. I will explain you more in detail. But it's one of the consequences in such cases is that you know, if you are a master of your trade and you are able to do calculation exactly analytically, as opposed to making small errors in your calculation, doing calculation exactly, you will get like incorrect prediction. But doing small errors, you will get the correct one. So bear with me, you will see how it comes about. So it will be about spectral properties of linear operators. I'm sure you are all familiar with why spectra are important, but let me just reiterate a few instances where we care about spectral properties. Well, quantum mechanics was sort of conceived, original motivation. One of the motivations was to explain a spectra of gases at high temperatures. For instance, if we discuss phase transitions, there are different approaches. Sometimes you can write partition function as trace of some transfer matrix, and then everything boils down to spectral properties, spectra of that transfer matrix. Perhaps even simpler, if you are at 0 temperature, then the only thing you care is, say, 2 lowest eigenstates as a function of some parameter. And then if, you know, depending on whether the gap closes or not, you have quantum phase transition, 0 temperature phase transition. We have heard several talks about quantum chaos and what that is. So one possible criterion, I mean, I wouldn't say a definition, but one of the simplest things that one often checks is so-called level spacing statistics. So it's again some spectral quantity. Also, spectral form factor, for instance, is just some other combination of eigenvalues where you don't care about eigenvectors, but you know, which can again tell you something about whether the system is chaotic or not. Even going outside of physics, say Markovian processes in general, actually my exact solution that I will later on talk about will be exactly this setting, just a Markovian setting. But for instance, many algorithms can be formed as some Markovian process. For instance, as an example, solving a system of linear equations. So you have some matrix A, and you want to find unknown x that satisfies that. Of course, solution in principle is just A to -1 acting on B, right? But that's not the way you would solve a system of linear equations, because calculating inverse of a matrix is first costly, numerically costly, and also unstable. So the way you do it is using some iteration. So you split A in terms of 2 matrices where you know how to calculate inverse of one of the 2. So Gauss-Seidel would be, or successive over-relaxation would be an example of such an iteration. And then you just iterate. Yeah? And the fixed point of this iteration is then the solution of your original equation. And so also here you see that basically you iterate m to the power of -1 on times n. So how fast your algorithm will work then boils down to the gap of this matrix, m to the power of -n times n. So I guess you believe me, right? Spectrum is important. Well, I will make now 180. This talk will be about cases where spectrum is irrelevant. So in particular, spectrum will give you incorrect prediction, as you will see. And such a, at first sight, a bit odd situation can happen if you deal with non-normal matrices. For instance, non-Hermitian. So non-normal, just to remember, are matrices that don't commute with Hermitian adjoint. So unitary or Hermitian matrices are normal, so everything is fine. You can sleep well if you're doing Hermitian and unitary matrices. But if you're dealing with non-Hermitian, non-normal ones, then it's good to have somewhere in the back of my mind this effect that I will tell you about, so that it doesn't bite you from behind. And in that case, you have to look at not the spectrum, but something which is called the pseudo-spectrum. I will tell you what it is. Another different view at what I'm going to discuss is going back to my previous slide and phase transitions. So in different settings, not just phase transitions, we are often interested in situations where a small perturbation leads to a large effect. So let me give you a sketch of under what circumstances that can happen. So let's take some linear operator and write spectrum and the composition of this linear operator. I'm deliberately writing everything in terms of still keeping track of left and right eigenvectors, because if this operator is not Hermitian, then, as you know, I have left and right eigenvectors which are not the same. Suppose everything is diagonalizable for a moment. Non-diagonalizability does not play a big role. Okay, so this is our operator, and now we would want to understand how much properties change if I add some smaller perturbations, and say epsilon times e. Then standard perturbation theory, which you are very familiar. If I write perturbation theory for eigenvectors, say right eigenvectors as a function of my perturbation epsilon, this is the lowest order. So the only difference compared to the more familiar Hermitian one is that here in the sandwich, this matrix elements is between left and right eigenvectors, which are different. Okay, so now I can estimate how large this change is. And I will look at the relative change in the jth eigenvector. So this is something just perturbation strength and this sum. In this sum, you have in the numerator, you have the norm of the left eigenvectors times the norm of the right eigenvector divided by the eigenenergy difference. So this thing can be big in two cases. One is if the eigenvalue difference goes to 0. This is a standard situation which we discuss in physics left and right. But for non-Hermitian operators, there is another possibility, namely that the numerator can also be large. In fact, it can happen that the product of these two norms diverges. So this is the situation that I'm discussing. But by the way, yeah, feel free to ask any question. Yeah.
The last line, what was LKR?
This one?
No, right side.
Yeah. Here.
Yeah. So what is LK and RK here? Are they?
Yeah, so index K numbers so say you have a finite matrix. So I have finite many left and right eigenvectors, and K just labels them, from 1 to,
So
I don't know.
they are eigenvectors, you're saying?
Right.
Left and right.
Okay. Right and left eigenvectors, yes. Yeah, correct. And now for Hermitian, of course, for Hermitian operators, left and right are the same, and they're both normalizable, and they're of norm 1. So the numerator for Hermitian guys is 1. Yeah. But for non-Hermitian ones, it can diverge. Diverge with what? Diverge in system size, the size of those matrices. So for the effect to be really interesting, as I announced it on perhaps in the title, I will really need like a thermodynamic limit, say, size of those matrices going to infinity. Yeah. Yeah, for non-Hermitian one, only one of them can be normalized. I will come back later, so perhaps I will sketch on the blackboard. So, yeah. Ask again. Any other questions? All right. Okay, so how can we get non-Hermiticity? We have seen non-Hermitian objects in several talks. For instance, Lindbladians would be one case. Transfer matrices in different situations would be another one. Tracing out some degrees of freedom would be one. Or doing coarse graining would be still another one. So the philosophy is I will start with unity evolution and then doing any of those things, you will, end of the day, end up with non-unitary, non-Hermitian guys. So in my concrete example is the following. So I have quantum mechanics, pure state evolution. I start with the product state. And then if my unitary propagator is sufficiently complex, like quantum chaotic, I mean, then eventually I should, at long time, reach something which would be similar to a random state. And what I would like to understand is relaxation. How do I get from this guy to this random state? In particular, how fast, for instance. You can quantify relaxation process by different objects. I will focus on purity, which is, from an analytical point of view, perhaps the simplest one. This is just trace of reduced density operator square. If you want a logarithm of that, would be Rényi 2 entropy. One could also look at out-of-time ordered correlation functions. The same phenomenology that I will show you for purity holds also for this one. And in order to be able to solve things exactly, at least in one case, my evolution will be given by a random circuit. So just 1D, a number of qubits, and then I apply gates in certain order, either, for instance, this brick wall or this, what I call the staircase. And those transformations are, with the analytical method, I can treat two cases. Either they're completely random 4x4 matrices if I'm discussing qubits, or it suffices if I take some fixed 2-qubit, this blue guy, to be composed out of a fixed 2-qubit unitary, like control node, for instance, plus single qubit random unitaries. So what I need is randomness on a single qubit for nice analytical treatment. Okay, and then because I have this randomness, I can average over this hard randomness and things simplify. In particular, equation for average purity is very nice. I just get some Markovian process of the sort that, say, a vector of purities, and by a vector of purities, I mean purity is an object pertaining to a given B partition, so I split my qubits into subsystem A and subsystem B. And there are 2 to the power of n different B partitions, because each qubit can be either in A or its complement. So I put all these different purities in a vector of purities. This is this volt I. And then there is this some Markovian matrix, which I can calculate for a specific protocol, again of size 2 to the power of n, if n is number of qubits. And the purity at time t is just this matrix to the power of t acting on initial vector of purities. So if I start with pure product state, fully factorizable, then my initial vector of purities is just all ones, right? Because purity for a product state is 1. And then, from here on, it's just a mathematical game, iteration of this matrix. Okay, and then you do it numerically and get a picture like that. So what would you expect? What would we expect? Expectation would be, so this Markovian matrix has one eigenvalue equal to 1. It corresponds to a long time asymptotic invariant state. This just corresponds to this random state reached at long times. So I will now, because I want to understand relaxation process, meaning how purity approaches this asymptotic purity, this relaxation should go with the next largest eigenvalue, right? Because this invariant state corresponds just to this one, which is lambda 2. There is a finite gap between 1 and lambda 2. Yeah? So something like lambda 2 to the power of t. Now here is what you get numerically, semi-log plot, time. Okay, this is not really purity, it's auto, but the purity would look the same. For certain system size, let's look at 34, you get this blue curve. If I plot lambda 2, I can calculate lambda 2, it's this green line, yeah, this exponential decay. So indeed, it is correct. If I take fixed system size and go with t to infinity, it's a very long times, I do get lambda 2 to the power of t. But you see, initially I have some other mysterious decay, which in particular is slower. If I look at the spectrum of my M, it looks something like that. So this is complex plane, it happens, it's real. It's not really important in this case, so those are eigenvalues. lambda 2, this green decay is this guy here. But my initial decay, it's given by this value. So there is no eigenvalue, I'm stressing this, there is no eigenvalue in the gap. And when we first saw this, we called phantom decay and phantom relaxation, because it looked like there would be some, as if there would be some fake phantom eigenvalue, even though there is no one. In this particular case, it's actually matrix is real, but it's not symmetric. So in principle, spectrum would be in a complex plane, and for some other cases, it is. Here I'm just showing the simplest one, which I will then solve it analytically.
Question?
Depends. So this concrete example is open boundaries, but you can have the effects in both cases, depending on the configuration of gates and so on. So it's,
Question. So how sensitive is this to purity? Like, do you see it in observables, local observables, or?
Yeah, that's a good question. We haven't looked much into that. So yeah. We know that it can happen for purity and orthoc. Yeah, for local observables, yeah, I'm not sure.
This lambda phantom, that should give a faster relaxation rate, but that one is a slower, you said, right? So
yeah, it's slower because it looks that this phantom mysterious is larger, right?
Right, yeah.
Closer to 1.
Oh, that's closer to 1. Oh,
yeah,
okay.
yeah. So,
okay,
sorry, yeah.
okay. Sorry,
this is like 0.
Okay,
1 is here, steady
yeah,
state. Yeah,
okay.
it's yeah.
Okay, so it's fast. It's a slower relaxation, but at long times that should.
At long times it goes, yeah, it goes into lambda 2. But yeah, important point now is, of course, one can say, okay, initially you have this some transient strange regime, fine. But now important point is that this transition time between this, say, phantom relaxation and lambda 2 goes to infinity. You see there are two different system sizes. As increased system size, this transition point moves further away. And this is actually very important for the effect to be really interesting, because now I can say, well, in thermodynamic limit, this transition point will move to infinity, and all I will see at every finite time will be this strange relaxation with kind of incorrect relaxation rate. So there is a related observation related in a sense that the gap does not predict relaxation rate. Also in Vladian dynamics, for instance, Takashi Mori has some papers, and there are some others. Okay, how can that happen? Let's go to back spectral decomposition. We write spectral decomposition of our matrix A, eigenvalues, right and left eigenvectors, and now coming back to the question about normalization. So for non-hermiticity, you can normalize, you have this B orthonormality, right, the delta J, K. But then on top of that, you can require normalization of one of the two, either left or right eigenvectors. So for instance, I can require that norm of right eigenvector is also 1. I can do that. But I cannot, on top of these two conditions, require also normalization of left eigenvectors. So left eigenvectors are left unnormalized. I can just demand two conditions. And in particular, it also holds that while you have this B orthogonality, left eigenvectors on themselves nor right eigenvectors on themselves are not orthogonal. So they still form a basis. Yeah, they span the whole space, but they are not necessarily orthogonal. So in particular, what can happen that as you increase system size, the angle between some of the, say, left eigenvectors gets smaller and smaller. So they get more and more collinear. And that's why those expansion coefficients that you get in this now spectral decomposition, writing purity at time t, gives you just lambda to the power of t times some expansion coefficients. These expansion coefficients are not anymore bounded by the norm of your initial state, as they would be for Hermitian matrices. They can in fact be exponentially large in matrix size. This is actually what happens. So these large CJs, if you want, mask the role of eigenvalues up to larger and larger transition time. And so, because this transition time goes to infinity, thermodynamic limit, this transient time is actually the relevant regime. It will give you correct physics. Somehow, one should have some method of extracting this phantom eigenvalue. This is what I'm going to show you. So here is one solvable case when one can actually do all spectral decomposition, solve everything exactly. The solvable case is the following. So gates are in this staircase configuration. So this is 1 unit of time. Every gate is a random Haar 4x4 matrix. This two-side Markovian matrix is actually has very simple form. There is single parameter alpha that depends on local Hilbert space dimension D. So I can discuss qubits, but also qubits. So D for qubits, this D is 2, but it works for any local Hilbert space dimension. Now in this case, I can do some simplification. Namely, I mean, this vector of purities, if you remember, it's exponentially large.
Those kind of non-symmetric matrix, one can, at least for OBC case, one can do the similarity transformation and make it symmetric, right?
Yes.
So then eigenvalues will become real.
But, right? Yeah, so I guess your question is where is the
where is that?
Where is the catch?
Yeah.
No, the catch is because this similarity transformation will be singular in thermodynamic limit. So in particular, it's not unitary, right? And so, yeah, in this case, a spectrum will be real. It's also in my case, it's real, but all the richness of the phenomenon is hidden in this similarity transformation.
So you are saying they will become singular as L tends to infinity, and you will see that feature in the relaxation.
Exactly.
And is that the, okay.
You will see sort of, I think, on next slide or two, how this goes more in detail. Yeah, so I have these 2 to the power of n purities for all different bipartitions, if you remember. Now I will focus from now on only on purities where I have a bipartition of, say, first k qubits and the rest. So I have these bipartitions of contiguous qubits. And there are only n such bipartitions, right? Because I can cut my chain after first qubit, second qubit, and so on, after n different places. It turns out that I can write separately iteration for only those contiguous bipartition purities, where sort of I reduce my Markovian process from this large exponential size to some size which is just for the n. This matrix, so iteration is like this. I will not go into detail. So there is some reduced matrix A, if you want, which depends on this matrix T, which is a very nice form. It's a Toeplitz matrix. So constant matrix elements along the diagonal, alpha square. First upper diagonal have alphas, everywhere 0 above that, and below the diagonal is alpha to the third, alpha to the fourth, and so on. Now, Toeplitz matrices, if you see a Toeplitz matrix, you should be happy because mathematicians know a lot of things about Toeplitz matrices. So in particular, for that one, basically I can write eigenvalues, I can write explicitly left and right eigenvectors, I can do everything. So I can do also this spectral decomposition to see explicitly how my expansion coefficients, for instance, explode, and how I, end of the day, get this phantom relaxation out of this spectral decomposition. Okay, so here is a bit dense slide. I will not go through the details, but just highlight a few interesting things. You can read more about it here. So this matrix, basically, I'm writing here everything in terms of A, but A is essentially this T. Yeah? So T is my matrix. It has very interesting properties. So this T actually has a spectrum is like that. So this is this real spectrum that I have shown you also in the plot on one of the previous slides. Then there is eigenvalue equal to 1 corresponding to the steady state. But half of this of the matrix dimension, so size of the matrix is of order n, but there is non-trivial kernel. Kernel is of size n over 2. So kernel is highly degenerate, so like if you want exceptional point. But for the explanation, actually it doesn't matter. So I can just focus on the non-zero part of the spectrum and do this spectral decomposition. You can go through the calculation, and at the end of your, doing some algebraic manipulations, you can get this effective decay, and you can show actually that indeed, out of these exponentially large coefficients, you get this phantom decay. So you get out of this calculation the correct number, which agrees with numerics. You can also look at the transition, how this transition from phantom decay into lambda 2 goes. There are some interesting scaling functions, but I will not go into details. So what you see out of this calculation is that this phantom decay is hidden in eigenvectors, which of course it's not very surprising, because if it's not in eigenvalues, where can it be? Well, it has to be in the overlaps. Somehow overlaps look something like that. So overlap of my initial vector with left eigenvector. If you do the calculation simplification, this phantom relaxation rate appears there. Also, you can do similar calculation for the kernel. Also in kernel, this phantom relaxation rate is hidden. Let me also say a little bit how left and right eigenvectors look like. If you imagine, yeah. Yes.
And then you should have the trouble defining this, right?
Yeah, okay, so in this spectral decomposition, there are no degeneracies, so only kernel is degenerate. So indeed, I can also do Jordan, and the degeneracy is such that there's a single Jordan block. I can also write sort of generalized spectral decomposition of Jordan block and do all the calculation. But to get my phantom relaxation rate, actually I can ignore this kernel, because kernel matter only for times less than n over 2. Right? Because
so does it mean for half of it you have one kind of normalization and half of it you have this? Because the standard normalization will be which you have imposed in the vicinity of the exceptional point. So you will separate those out, and for that you do a different mathematics. But what about the mutual space?
So I can split my matrix to a kernel, right? This degenerate subspace and the rest. So for the rest, I have all the standard things and left-right eigenvector standard normalization. For the kernel one, I can write kernel in terms of generalized eigenvectors, which is just the basis where you have the standard form. Right.
My worry is you have this vector space or this vector space,
Yeah.
but then you have some mutual
right, they mix.
Angle.
Indeed.
Yeah, that's where I think the interpretation will come.
Yeah. So, okay, I don't have a picture here, but if I try to now calculate my purity as a function of time, right? So here there is time of order n over 2. So I start with 1 and then I somehow decay. So from this time onward, I can forget about the kernel, because this kernel part to the power of n over 2 is 0. Yeah? So here I get correct decay, whatever it is. In this first part, indeed, the two mix, and so I have to correctly take into account kernel and spectral decomposition. I have also cross terms. But somehow out of this spectral decomposition, actually, perhaps I can explain you more in detail later on. Actually, in spectral decomposition, you get some diverging term. They diverge in thermodynamic limit. In fact, it turns out that the kernel part, including this mixing between kernel, exactly cancels out this diverging term. I don't know why, but it's somehow magically, it's some, sort of, like we often do in physics, yeah? If you get infinities, you forget about them. Here it's again the same situation. Okay, so somehow out of this mysterious phantom eigenvalue appears. Still, the question is, okay, in this case, I could do calculation exactly. But still, I don't know what is the object that gives me this phantom decay. Okay, lucky for us, For Toplitz's matrices, there is also a well-defined notion of Toplitz's operator, meaning like the operator infinitely sized matrix if you want. The easiest way to discuss Toplitz's operators is in terms of so-called symbol of a Toplitz's matrix. Symbol of a Toplitz's matrix is nothing but the Fourier transformation of those matrix elements along the skew diagonal. So in the language of a physicist, this would be called Bloch Hamiltonian, if I would have periodic boundary conditions. I don't have it. So if you have a symbol, then basically if you evaluate this symbol at the unit circle, for my case, I can calculate what is the symbol. It's just this simple function. And symbol evaluate at unit circle gives me this egg-shaped object. This is the spectrum of an operator. So the spectrum of an operator, meaning like a, naively infinitely sized matrix, is this oval-shaped object. Spectrum of any finite size matrix, finite size representation of this operator is this red line here. So you see? And the phantom relaxation rate is nothing but this thing here. So the largest eigenvalue in the spectrum of the operator. And the spectrum, you see, it's discontinuous. So spectrum of any finite size matrix is completely different than the spectrum of an operator. So this funny effect comes about due to operator having quite different properties that finite size matrix representation of that same operator. All right, well, very well. But in this case, I was able to calculate the spectrum of the operator only because, yeah, I had this Toplitz form and everything is solvable. So still the question is, okay, what about cases that are not solvable? How will I calculate the spectrum of the operator in that case? And there is a very nice answer. It is, you have to look at something which is called the pseudospectrum. So let me explain you what is now a pseudospectrum. So there is a very nice book about it, and there are several equivalent definitions. So there is a notion of epsilon pseudospectrum. One definition of epsilon pseudospectrum would be like points in complex plane Z where resolvent is very large, larger than 1 over epsilon. Another one equivalent would be where the smallest singular value of this Z minus T, T is our matrix, is smaller than epsilon. So like, I'm almost singular. Another one would be, and this is like a nice way to visualize, is it's a spectrum of slightly perturbed operator. So I take some perturbation E, say normed matrix less than 1, and then pseudospectrum would be union of all such spectra running over all normalized perturbations. Nice thing about this pseudospectrum, epsilon pseudospectrum, is that in the limit n to infinity, pseudospectrum is independent of perturbation strength epsilon. And here is a sketch. So again, the same case. And now if I calculate spectrum of slightly perturbed matrix, this is what I get on the right-hand side. So I take epsilon 10 to minus 15, so very tiny perturbation on the level of floating point rounding errors if you use double precision. And then I look at the spectrum, numerically calculate spectrum for different system sizes. You see, as I increase system size, you see that this slightly perturbed spectrum actually goes to the pseudospectrum, which is equal to spectrum of an operator, corresponding operator. And therefore, this is from the title now, if you calculate your spectrum exactly, you get these red dots, which give you lambda 2, incorrect prediction. If you do this slight numerical rounding error, you get a pseudospectrum, which gives you a correct prediction for phantom decay. Statement of
sorry. So here T is still Toplitz, is it?
Yeah, the same Toplitz that I've shown you. Yeah, this numerical example is for this same Toplitz. Yeah.
Okay, thanks.
Okay, you can ask a question of how small, or how, for instance, for given the order of limits here matters. You should take first n to infinity and then epsilon to 0, and these limits do not commute, you can ask yourself, okay, for given epsilon, how large should my n be in order to be close to the pseudo-spectrum, close to the spectrum of an operator? This depends on the matrix, but for my very simple example, I can argue and show using the general perturbation theory of this kernel. Here actually kernel matters, because eigenvalues in the kernel are very unstable. Let me perhaps just show you on a simulation here. Yeah, I will finish in a minute. So here is simulation, increasing epsilon, having one realization, no averaging here, how this spectrum evolves from the unperturbed one to the perturbed one. You see, because this kernel was highly degenerate, degeneracy was n over 2, like half of the matrix size, it's very unstable to perturbation. And so you have this Poisson series of radially emanating eigenvalues then colliding with other ones and unzipping spectrum into this pseudo-spectrum. Yeah.
In this process, what happens to the eigenvectors? Is it smoother?
I haven't looked into that one, but I know that eventually eigenvectors of this guy, a bunch of them becomes more and more collinear. So also perhaps a comment about the eigenvectors. If you plot them how they look like, they become localized actually at the edge. So left eigenvectors are localized at the right edge, right eigenvectors at the left edge. What is called the non-Hermitian skin effect in some other context. Okay, perhaps I can discuss this if there are any questions. So there are other instances where pseudospectra are important in physics, but let me perhaps leave these to questions and just show you a summary. So if you're dealing with non-Hermitian matrices, be aware that it can happen. It doesn't happen always for all matrices. That gap, or the second largest eigenvalue, does not necessarily give you a correct relaxation rate. Limits t to infinity and n to infinity do not commute. Yeah, this transition point goes to infinity. What you should look at is something called a pseudospectrum. And there is a, if you want like a one-liner take-home message, there is a funny, here's a funny quotation from this nice book, which I very much recommend, about the properties of non-normal operator. It says, in the highly non-normal case, vivid though the image may be, the location of the eigenvalues may be as fragile an indicator of the underlying character as the hair color of a Hollywood actor. Yeah, so don't judge matrices by their spectra. Thank you.
Any questions? More questions.
So this, the perturbation, the matrix E that you put, epsilon E, right? What was E, and is it sensitive to the choice of E? Like
yeah, so here, this concrete example was, okay, I take this epsilon, and then the perturbation matrix E was just a matrix of random Gaussian real numbers of variance 1.
Okay. Do you think it's sensitive to that choice, or?
No, yeah. No. So, okay. Like in the limit n to infinity, for generic perturbations, you will get something which will look very close to pseudospectrum. So like one instance is enough. It's kind of self-averaging.
Yes, I think I remember that a situation like this, but without doing what you did, but the non-Hermitian matrix comes in the, when you're calculating a Lyapunov exponent, you do the monodromy matrix, but that's not the rule. The rule is you have to multiply it by transpose and then diagonalize. And I have the impression that if you look at the eigenvalues of the monodromy matrix without multiplying it, but by the transpose, you get into trouble.
Yeah.
So it may be a, are you aware that?
Yeah, good question. I'm not, I don't know whether actually it's the same problem. Perhaps related comment, I was just looking a few days ago papers about Ruelle-Polycott resonances, yeah, because there, again, you do truncation or small noise, and then you get some non-Hermitian matrix whose eigenvalues you want to understand. And then in some cases, people have observed actually then how stable those calculations are can depend on which basis you write your operator. So my sort of speculation is actually that in some of those cases, one might actually be dealing with this, pseudo-spectrum versus spectrum. The two are different. For normal matrices, the two objects are the same, so there is no problem. Spectrum is the same as pseudo-spectrum, but sometimes they can be different from non-normal ones.
So in the relaxation, these eigenfunction or eigenvectors, they are entering. Otherwise, because as I asked before also, PBC versus OBC, would you see both cases such?
So for instance, this solver case was purity for OBC in this staircase configuration.
Sorry, can you repeat?
Was for purity evolution with staircase configuration of gates and open boundaries. So if I would look at OTOC and brickwork circuit with periodic boundary conditions, I would also have similar effect. So kind of, I'm not able to tell upfront whether, in a specific situation, depending on boundary conditions, configuration, and so on, I will or not.
No, because I'm asking again that similarity transformation does not work for PBC. It only works for OBC.
It depends really on situation we can discuss.
Okay,
it's not like that there is a general rule.
I'd like to.
Yeah.
Okay, so I think we can thank Marko again.